What if the story we tell ourselves about the universe isn't the whole story? We're going to dive into a fascinating new idea today, one that challenges our most basic ideas about reality itself. You see, for decades now, we've had this reigning champion in the world of cosmology. It's called the Lambda CDM model, or LCDM for short. And look, it's been the champ for a reason. It's been incredibly good at explaining just about everything we see out there. But lately, our best telescopes have been spotting some weird stuff. Annoying little puzzles in the data that just don't quite fit. It's almost like the champ is starting to show its age, you know? A few cracks are starting to appear in the armor. And as these puzzles keep piling up, a bold new challenger has stepped into the ring, claiming it can solve these mysteries and paint a much more complete picture of our universe. So for this explainer, that's what we're going to do. Break down this cosmic title fight, the reigning champ versus the new contender. Okay, let's get into it. First up, we need to take a closer look at our reigning champion, the Lambda CDM model. Now this model is a heavyweight for a good reason. It does a beautiful job explaining the afterglow of the Big Bang, what we call the cosmic microwave background. It explains why the universe is expanding, and it nails why galaxies clump together into the massive cosmic web we see. But, and this is a huge but, it only works if you accept two ingredients we have never ever directly seen: dark matter and dark energy. Plus, to make all the math work, it needs this idea called inflation, this mind-bogglingly fast expansion right at the very beginning of time. All right, so now let's meet the challenger. It's called dynamic vacuum field theory, or DVFT for short. And this theory, well, it proposes a radically different way of looking at the very fabric of space. So here is the absolute key difference between the two. In the standard model, the vacuum of space is basically an empty stage. It's just the passive background where all the action happens. DVFT comes in and says, nope, not even close. It says the vacuum isn't empty at all. It's a real physical substance, kind of like a cosmic superfluid. It's not just the stage, it's also one of the main actors. And this brings us to the core idea of DVFT, something called vacuum coherence. Imagine this cosmic superfluid is like a vast, stiff gel stretching across the entire universe. The theory says this stiffness is so powerful that it keeps the properties of a universe perfectly synchronized, even over billions of light years. And if that's true, this one idea could solve the puzzle of why our universe is so uniform everywhere we look, without ever needing that inflation idea. So it's a pretty radical idea, right? But how does it hold up against the actual evidence? Well, let's head to round one, the universe's first light. What you're looking at here is the cosmic microwave background, or CMB. It's literally the baby picture of our universe, an image of the cosmos when it was just 380,000 years old. Thanks to the incredible data from the Planck satellite, we've mapped the tiny temperature fluctuations in this light, which basically gave us the blueprint for every star and galaxy that would come later. And here's the thing, when you look at the main features of this data, the big peaks and valleys, both the champion, LCDM, and the challenger, DVFT, they both match it incredibly well. On the surface, you'd have to call it a draw. But the devil's in the details. And this is where DFFT claims to have an edge. It predicts very specific, subtle differences in the data. When we look at the largest patterns in the sky, DFFT predicts about a 10% boost in power. And for the very smallest patterns, it predicts a 5% suppression. And get this, those predictions actually line up with known anomalies in the Planck data. Little glitches that scientists could never quite explain. What we thought were random quirks might actually be a natural consequence of vacuum coherence. All right, round one is looking pretty interesting for the challenger. Let's move on to round two. We're going to fast forward from the baby picture to the universe's awkward teenage years, the era when the very first galaxy started to form. The James Webb Space Telescope has been staring deep into the past, and it has found something truly shocking: galaxies that are just way too big and well-formed for how early they exist. According to our standard model, there simply shouldn't have been enough time for them to grow so mature. That's why they're being called impossible galaxies. And this is where DVFT comes in with another strong jab. Because the vacuum itself is an active player in this theory, it naturally predicts that galaxies should form faster. So, when you compare the predicted distribution of galaxies from DVFT to what JWST is actually seeing out there, the alignment is pretty compelling. And we're not just talking about some vague, it's faster idea. DVFT predicts a specific 20 to 30% increase in galaxy density way back then. This is a solid quantitative prediction that directly addresses one of the biggest surprises coming from our most powerful telescope. So, after two pretty intense rounds of evidence, what's the verdict? Let's take a look at the potential scorecard for this new challenger. What makes DVFT so compelling isn't that it just solves one problem. It seems to elegantly connect several of cosmology's biggest puzzles. It matches the CMB data and potentially explains its little anomalies. It addresses the impossible early galaxy problem. And it even offers a potential way to solve the famous Hubble tension. It does all of this with one core idea, the dynamic vacuum. And in the process, it gets rid of the need for both inflation and dark matter. That's a huge deal. Now, let's be clear, this theory is still the challenger. It has a lot more to prove. But it leaves us with a really profound question. For decades, we have been looking for exotic new particles and mysterious forces to explain the cosmos. But what if the answer wasn't in adding new things? What if it was in fundamentally rethinking the empty space that's been all around us all along?